Hello and welcome to the second part of our seventh and final lesson in our fourth unit, Graphing Quadratics, in our grade 10 academic math class. So this second part is now going to be creating equations of quadratic relations in factored form. And as you know, we have it right here at the top, we have our factored form version of a quadratic relation. We'll notice that the things that we're going to want to be able to substitute in to build this equation are our a value, our s value, and our t value. The x's and y's will just stay in there. Those will always be our input and output values. So we need to have a, s, and t in order to do this. So let's start with example 2. We're just going to look at some scenarios where we can build this equation of a quadratic relation in factored form. Given certain situations. So let's have a look at our first one. So we have y equals a bracket x minus 3, x plus 5, and negative 230 is a point on the parabola. Okay, so in this question we don't actually have our a value, but we have the means to find it, meaning that we have our s and t values at positive 3 and negative 5. And we can substitute in the x and y from this point we know is on the parabola in order to determine a. So let's do that now. We are going to, in the place of our y, we are going to substitute in 30. A is our unknown variable. X from our point is negative 2 minus 3. And x, again, from our point is negative 2. And now we have our plus 5. And so now we are going to simplify this and then isolate a. So let's start by simplifying the contents of those brackets. That will give us negative 5. And here we have positive 3. Our next step is to multiply those two values together. That will give us negative 15 a's. And how do we isolate a? Divide both sides by negative 15. And that will result in our a value of negative 2 showing up. And now we restate the equation of the quadratic relation. So we would say, therefore, we have y equals negative 2 to replace our a. The x's stay the same, so x minus 3 and x plus 5. And that is our quadratic relation in factored form, having found our a value using another point we know to be on the parabola as our x and y values to input into the equation. So there's our first example. Let's look at the second one. So this parabola has zeros of negative 2 and 4 and a y-intercept of negative 4. So let's sketch this one. Okay, so again, we're trying to build a quadratic in standard, or rather in factored form. It looks like this. Y equals a, x minus s, x minus t. And they've provided us with our s and t values right here. So we can actually substitute those in right away into our equation. So we've got y equals a, x. Now again, it's the opposite of how they appear. So this is minus minus 2, so that'll be a plus 2, and minus positive 4, so minus 4. So what we're missing in this case again is our a value. Last time we substituted a point in order to determine our a value. We can do the same thing here because our y-intercept being at negative 4 is sort of a tricky way of presenting two values, because our y-intercept, if we were to write it out, would be 0, negative 4, which we can use as our x and y values to determine a. So let's do that now. We're going to substitute in negative 4 for our y. A is our unknown variable, 0 is our x value, plus 2, and 0 minus 4. And now, working along, we're going to evaluate, so we're going to simplify these brackets. That'll be 2, that'll be negative 4. We'll multiply that side out, so we end up with negative 8a. We isolate a by dividing both sides by negative 8, so that's going to give us 1/2 equals a. So now we can build our quadratic equation in factored form by replacing our a value and keeping those other two. So they were plus 2 and minus 4. And there is our quadratic in factored form. Now we're also going to sketch this one, so let's get some of these values onto the graph, shall we? So we have provided for us -2 and 4 as our x-intercepts. We've also been provided with our y-intercept, and our y-intercept was given to us at -4. So there's our -4 right there. And from here, we can actually start to fill in some of the pieces that we don't have. Now, we can do this algebraically for sure. I'm going to do it today just based on a visual confirmation of where my axis of symmetry should be. So there's my axis of symmetry. That's hanging out at x equals 1. So that's looking pretty good so far. Our parabola opens up, which we know, so this is looking pretty good. We do need to figure out where our vertex is going to be. So how do we do that? Well, we take our value for our axis of symmetry, our h value, and we are going to substitute that into the equation that we've built. Now, I haven't left much room for myself to do this, so I'm just going to kind of tuck that in right down over here. So we have y equals 1/2, and this is the x value we have, so x plus 2 and x minus 4, and we are going to figure this out. So we've got 1/2, that's going to be 3, and that's going to be -3, and that's going to give us -9 halves as the y component of our vertex. So -9 halves is basically like half of -9, which is -4.5, so we're going to put that on here. Is it kind of weird that it's 0.5? Yep, there's nothing wrong with it. So we're going to go down 1, 2, 3, 4.5. There we go, that's our vertex. And this actually makes sense, because if we consider that our plot pattern is normally 1, 4, 9, let me scooch that over a little bit. So normally we've got 1, 4, 9. When we go out 1 unit in either direction from our vertex, or out 2 units in either direction from our vertex, or out 3 either direction from our vertex, this is now amplified by our a value. So this makes sense. Normally we would go out 1 and up 1. Now we go out 1 and up 1/2. And instead of out 2 and up 4, we go out 2 and up 4 times 1/2, which is 2. And instead of going out 3 and up 9, we go out 3 and up 9 times 1/2, which is 9 halves, or 4.5. So let's do some graphing now. There's our vertex, out 1 and up 1/2, out 2 and up 2. That's there. And then out 3 and up 4.5. So this is our graph. Let's put a line through it, make it as curvy as possible. That's looking nice. Get some arrows on there. Let's get some labels on here. So there's my vertex at 1, -4.5. And let's get our x-intercepts on there. That one is at 4, 0. This one is at -2, 0. And our y-intercept is at 0, -4. Oh, and the equation. So y equals 1/2 x plus 2 x minus 4. Made kind of a mess of it, but that is what we need to do here in order to graph this quadratic from factored form. Okay, one more example. So this parabola has zeros of -5 and 3 and a maximum/optimum value of 6. Okay, so again, we're trying to build our parabola, or our quadratic, in factored form, which means that we need a and s and t. So we actually have a couple of these values already. They've told us the zeros. So we've got -5, which will be -5, so +5, and 3, which will be x minus 3. So now we have a couple of pieces. We also have here a maximum optimum value of 6. So what this means is, if you recall, our optimum value is either, sorry, I guess it says it's a maximum. So we have a maximum here, a highest point of 6. That's going to correspond to our vertex. Now our vertex actually has two components to it. It has the high part, which is 6, and then it has the h value, which is our axis of symmetry. So fortunately for us, we can actually, I'm just going to erase that since that's just meant to be a visual aid, we can actually find the h component of our vertex by finding the algebraic halfway point between h and between s and t rather. So we have minus 5 plus 3 all divided by 2. That gives us negative 2 over 2, which gives us negative 1. So we actually have a vertex in this question of negative 1 and then the provided maximum value of 6. Looking great so far. Now we have another x and y value to substitute in to figure out what our a value happens to be. So let's do that substitution now. Our y value was 6, a value is still unknown, and x was minus 1. And we're going to substitute that in for both of our x's. I think that was right. Yep, minus 1 and 6. And now we're going to simplify the contents of the brackets. That'll be 4. That'll be negative 4. Going to keep going here. Trying to save a little bit of space. That'll be negative 16a. And we can divide both sides by negative 16. And that gives us, so if we were to divide both the numerator and the denominator by 2 to reduce it, we would end up with negative 3/8 equals a. There we go. And now we are going to do our rewrite. So again, I didn't space this very well, but I'm going to go do my rewrite all the way on the other side over here. So we have, as our final answer, therefore, y equals negative 3/8 bracket x plus 5x minus 3, I think they were. Yep, that looks great. So there is a slightly more involved version. Again, just to recap that, in this last one, we knew the maximum optimum value was going to be our vertex, so we found the h value to complete that point and then substituted it in to get a. In the example above it, we were provided with a y-intercept, which again, once we consider that that is actually 0.0, negative 4, we could substitute that in to get our missing a value. And the example above, it just gives you the point straight away. So they're all occasions where we're finding the a value using other points and then building our quadratic relation in factored form once we have the a. So that's our last lesson in Unit 4, Graphing Quadratics. By all means, listen to these lessons again as we prepare for our assessments and as we do our homework. If you have any questions, you can reach out via email, and otherwise, good luck.